This lecture is being brought to you in part by the generous gifts of these sponsors.
Let's see. Good evening, everyone. Thank you very much for welcoming me here. Surprisingly, I've been with IHMC for close to 10 years, and this is somehow the first time I've managed to make it down to Ocala, which is unfortunate. I've really enjoyed my time here. One of the things I was also surprised by was when I walked in, the number of pictures you all have of some of the robots that we've built, and then also thinking, wow, we really need to get them some new pictures because we have some new robots. So as Lori said, I did my PhD at Virginia Tech. I'm originally from Chattanooga. One of the things I did my PhD on was actually firefighting robots. Brought me down to the Gulf Coast. So we actually took one of our robots, which you can see here on the right-hand side here, and used it to put out a fire on board a ship, which was pretty cool. So a real fire. One of the convenient things that you learn there is, how are we going to fireproof this robot? I know. Let's go to Cabela's and buy a triple XL rain suit. That works pretty well. But I also thought that it would be appropriate to really bring down one of the devices that we worked on. That's really what brought me to IHMC. So here on the other side, you'll see our exoskeleton, Mina V2, and that's what got me first involved at IHMC, was being able to join the team to do a lot of the software and locomotion for our team that we took to Zurich to compete in the Cybathlon in 2016. Before I get going any further, I do want to also say one of the great things about working at IHMC is I'm privileged to be able to work with a fantastic group of people. So this is most of our robotics team. Not everyone on the team is actually pictured here, but as you can see, these are all amazing individuals that are committed to this kind of research just like I am, and we wouldn't be able to do all of the things that we do, and I wouldn't be able to show you all these wonderful things if it weren't for these people who really make it happen. So let's dive in. So I'm here today to talk to you all about humanoids, how we're using them, what we think they're going to be able to do, but I think it's important to understand why I care about this as a subject. And really it's because most of the existing robots that are out there, if we think about how robots are currently used today, whether it be robots that vacuum your floor or robots that help make your car in a manufacturing setting, those are really designed for one purpose only. They aren't multi-purpose, they can't go very many places, they can't do very many things. They really fail in all kinds of environments, and there's all kinds of things we want robots to be able to do. Whether that be go into a nuclear facility and be able to address challenges in a control room, like was actually needed during the Fukushima nuclear disaster, or do the more boots on the ground of disaster response, so actually go to one of these emergency sites and be able to navigate this, or to be able to help remove troops from dangerous environments where we really don't want to be sending people if we can avoid it. But these have all of these challenges associated with it. There are doors that get in the way. I mean, how are you going to fly a drone in if there's a door in the way? Ladders, control panels, rubble, things like that just prevent our normal robots that we have now from being able to do this. But it really kind of begs the question of, well, why humanoids? Hopefully by the end of the night, you're not going to be wondering that. And I like to say that it's really because we want to make robots that can go where people go and do what people do. Right now we have people doing all of these tasks that we just called out that we maybe don't want them to be doing in the long run. And these robots, as you can kind of see here, they're incredibly capable. We can do all kinds of different things with humanoids because of their form. And this, I think, is also really illustrated when you start comparing them to other types of robots, other types of mobile robots. So if I think about this kind of comparison, where let's say I'm going to take a biped, so humanoid with two legs, compare it to a quadruped, like a robot dog, as well as a wheel robot, a robot with tracks, and I want to put them into different scenarios. Let's think about like gap crossing and barriers. I need a pretty tall quadruped if I want it to be able to go over a long gap, like what a human can, or over a barrier, like a human can. Your wheels need to be huge. It's your wheel radius that's going to limit this. Fortunately, on slopes, all of these do pretty well, so maybe that's not a great example of why humanoids can do them too. Ladders, though, if I have wheels or legs or tracks, I can't really climb ladders very well. Quadrupeds can. We've actually seen quadrupeds be able to do this, as well as dogs. If you actually Google dogs climbing ladders, you'd be kind of surprised. But I would argue that humanoids do this probably the best. But then it starts to get a little bit more interesting. So we said on the other ones, you probably need a pretty big robot. If I start thinking about more confined spaces, if I wanted to be able to squeeze between a platform, well, humans can turn sideways. maybe as Lori was saying, since I've had 2 little girls, I can't quite squeeze between as tight of a narrow passage as I used to be able to. But we're pretty skinny where we need to be, whereas we can be wider at the shoulders. And then the same thing applies to fire poles. So whereas if I'm a quadruped or a wheeled robot or a tracked robot, they have to be really narrow, really small. So the same robot that can do tight passages can't go over big gaps. Same thing with rocks. Same robot that can squeeze between poles can't go over big rocks. And then, the great thing about humanoids is they really only need space on the ground about that big, maybe every 3 feet or so, to be able to put their feet. And they can walk over that. Whereas a wheeled and tracked robot just can't. And a quadruped is going to be more limited because it has to figure out where it's going to put all of its feet. You can actually take this and put it in my former colleague's garage, which we can call a disaster zone. And you can see a great illustration. So you can squeeze sideways between here, step over onto a desk that I maybe haven't seen since school in the 90s, onto a ladder, and then walk across a carpet that's about balance beam to get a tennis racket out. And I'd argue that unless you can fly over there to go get this tennis racket, you're probably not going to be able to get there with wheels, tracks, or even 4 legs. And you really can't get through a space like this without bipedal mobility. And this is what I think is really powerful. There's not a lot of places that humans can't go and things that humans can't do. And this has led to a lot of development over time and investment from government research in this space. You can see all of these different platforms that have been developed throughout the last 25 years. IHMC is on there in a couple different places, probably because I represent IHMC and want us to be on this timeline. But also, you have some of these big systems like, let's see if I can get my cursor going. You have the Big Dog platform, which really led to LS3, and that ends up leading to the building of these huge companies like Boston Dynamics. Some other things, some really highly mobile systems like what we got out of this M3 challenge here, which literally kind of captured this public imagination of, well, what can we do with these running platforms? And then we have my PhD right here of shipboard firefighting. And this all kind of led up to the DARPA Robotics Challenge. And I will still say that I think that the DARPA Robotics Challenge is probably one of the greatest demonstrations of legged robots today. While, I'm going to say that not only because IHMC came in second. I think that one of the big things when you compare this to a lot of what we're seeing now with humanoids, we're seeing these amazing demos, is at the DRC, you had to show up. You'd never seen the course before. You didn't know what it looked like. You didn't know exactly what you needed to be able to do, and you had to show up at a specific time and do all of these tasks, drive a car, go through a door, turn a lever, flip a switch, some mystery task, go over terrain and up some stairs. You had to do all that within an hour. It's a long time to do that as an hour, but not for a robot. And you get one chance, and the next day you get another chance, but if you can't do it in one of those days, you're done. That's not like what a lot of our demos are today. On those, you can record them over and over again until you get the right take. However, this success has really kind of led to the development of startups. There's a lot of companies now that are looking at, well, the capability of these robots, what can we do with them? This is a huge list now, particularly when you start counting some of the companies that are emerging in China, like we have on here just 2 of them, Fourier and Unitree, but there's quite literally hundreds out there in China. But other companies like some of you may have heard of, Boston Dynamics, Apptronic, Figure AI, these are all around this idea of really taking advantage of these different capabilities that humanoids have. The ability to get into tight spaces. They don't really care about the extreme mobility. They care about the confined space. This large workspace that you see here, the ability to reach up high as well as down low on a humanoid, and then the ability to use tools and interact with the world. It's really about this kind of idea of mobile manipulation. It is important, I think, to note, though, that as of right now, at least in the United States, the only real one of these companies that you can buy the robot or a company's using the robot is Agility Robotics. And that kind of starts thinking, well, what are the applications for some of this? You could say logistics. So this is Agility here. And one of the ways that they looked at deploying their robot, Digit, is to be able to move these empty totes for Amazon warehouses. So after you've had your fulfillment center where your packages have been moved, the robot can go get it and move it back to be filled up again. I'm not 100% sure why you need legs for this task. I think that that's kind of an open question. I think really we're going to talk about that a little bit more in a minute, how they're justifying that. But you can make an argument that legs aren't needed, but it gives you the huge workspace, so that's nice. You can also look at manufacturing. This is a big area that people are focusing on. There's a big worker shortage in the United States, where even the number of people who are unemployed, if you compare that to the number of open jobs, we actually have more open jobs than we do unemployment. So even if all the unemployed people were employed in these jobs, you wouldn't have enough. So there's this question of how you would use that. One of the companies or sectors that's been kind of leading this is automobile manufacturers. So here you actually have the company Agibot on the left. They're a Chinese company who they're using this robot to do assembly and inspection on these lines. And on the right, you have the Figure AI company who's integrated it into part of the BMW manufacturing line in North Carolina. So it's mainly placing things on the line, steps back, lets it go. And the robot's not a bottleneck in this path because it's a relatively slow task, so they don't need it to be fast. One of the other areas that a lot of people are now going after, and I think that this mostly has to do with the size of the potential market, is the home. So thinking about how can we have these humanoid robots be built for this environment. So this is a company called 1X. They're started out of Norway. They now mostly relocated to San Francisco. This is their robot Neo, doing a number of different tasks. And their argument is there's all kinds of things that we want these robots to do in the home. And the first time they made this argument, they were talking about, wouldn't it be great if you had a robot that could wash your dishes? And my mind immediately went to, well, we do. It's called a dishwasher. But the point stands. There's all kinds of tasks that we all do in our house that we probably don't want to do. That's why Roomba exists. And I think that really what a lot of this boils down to is that humanoid robots are meant to be general purpose. The capability provided by just the form factor, this morphology that we have as humans. We've built this world around us. We built our tools for our hands. We built our stairs for our legs. We built our doors for our bodies. If we want a robot to move around in that space, it's going to be probably pretty close to looking like a humanoid if we want it to be effective. And then I love this quote by Andrew Carnegie, who talks about how it boils down to, you could say, I'm going to diversify my investment set, build all these different robots, or I can just build one really good robot. That has a lot of advantages because then you only have one that you have to design, manufacture, and support. This idea of supply chain, you only have to solve that once. You get the economies of scale. It's a whole lot cheaper to build 100,000 robots than 10,000 robots. It's probably cheaper to build 100,000 of one than 10,000 of different kinds. And then they can, part of it is also if you can give these things intelligence, they can tackle a large number of different tasks. So I guess what we're now going to dive in on is, well, what does it take to actually start to do some of this? And now I get to lean on a lot of the work that we've done at IHMC. I'm going to sprinkle in some stuff done by other people as well because I don't want it to be wholly about us, but I'm your speaker, so I kind of get to choose whose work I'm presenting. So what does it take to go in to build a humanoid? We have the traditional component that a lot of people think of, the hardware design. So here we have our robot Nadia. You can see we have to put perception sensors on there. You have to have different actuators, which make the joint move. You have the mechanisms that go into those joints, end effectors or hands. We have shells that we put on the robot to protect it. But beyond the hardware design, there's all kinds of additional parts to it. If I build a platform, I have to make it actually do something. I need to have good controllers. I need to have behavior algorithms. So how do we make it make decisions and do the autonomy aspect? But also, what if I don't want it to make the decisions? What if I want to tell it exactly what to do? I need to be able to teleoperate it. And then how do you interface with this thing? There's all kinds of these challenges that each of these companies has to solve. Typically, they're solving them independently. Most of them aren't really working together. They're leveraging all the research that we've done, but they're still having to build this up themselves. And I would say, the first parts of this is this idea of compliant actuation. I think that this is kind of a core part of it that in the last handful of years, we've actually started to figure out how to do, and that's one of the reasons that you see these robots kind of blowing up. And what I mean by actuation has all these requirements. It needs to be high power, it needs to be low weight, it needs to be fast. But I think that compliant aspect is important. What I mean by that is, if it interacts with the environment, I don't want it to just bust through whatever it hits. I want it to comply. I want it to have some give, which I think you can see here really well. This is a KUKA robot arm. These spun out of DLR, which is the German space agency, many, many, many years ago. And these are some of the first platforms that really said that this is going to be a core part of our business. And you can see that as this person interacts with it throughout this video, the robot gives. It doesn't just push through him, which is very different than the classical approach that's used in a lot of automotive manufacturing, where it just says, I'm going to go to this position, and if you get in the way, I'm going to move you, which isn't good if you want this robot to be operating with and around people. It's not safe. It's also not safe for the robot. You know, it can break the world around it, but it can also break itself. And if I start looking at this, human muscle is great at all of these things. You can make incredibly strong muscle. I bump the table, my arm moves. It's also light, and then it can be really fast. So I think we have this thing that we call this kind of speed-torque curve in motor land here on the right-hand side that you'll see again here in just a second. And human muscle is really good at getting that high force at low speed and then those really high speeds at low force, which is what this curve here is. Ways that we actually achieve this compliance, there's a couple of different ways that we've done over the years. The first is one thing that was actually kind of pioneered at IHMC after MIT, which is this idea of series elastic actuation. And what I mean by that is actually taking a spring, an elastic element, and putting it in line with my force transmission. And what that does is it's kind of decoupling your motors and everything from the way it interacts with the environment. So if I hit the world, it doesn't make my motors move because I have that nice soft spring. That has that advantage of both being compliant in its interaction, but also doesn't break the motor if I hit it on the world. And this is what we used during the DRC for my team at Virginia Tech. This is our robot here that we built ourselves, Escher. And we used series elastic actuators all over it. A little bit different than what IHMC had built in the past, this M2V2 platform here, which you ever do come up to Pensacola, that's in our lobby. The problem with SEAs, as we call them, is that they aren't very fast. And that was one of our core requirements, right? We said we wanted to be able to make sure that we could do high speed. We don't just want compliance, we want high speed. And to that end, one of the other ways that a lot of people traditionally did this was hydraulics. If you've ever seen a lot of these backflipping robot videos that came out, that was using this robot here, Atlas. It used hydraulics on it. And we used hydraulics on Nadia too. We used these things made by Moog, this integrated smart or servo actuator. We had 12 of these all over the robot, which you can kind of see highlighted there on the far right-hand side. And these just have an incredible amount of power in them. And this is primarily because it all goes through the pump. You have one big pump on the robot, which we'll talk about why that's a problem here in a minute. I mean, if I take my muscle curve that we had, which is this line that goes right here. I'm not really good at the pointer. So this line right here, if I compare that to our hydraulic valve, which limits it, you can see we actually get more torque density out of this guy than human muscle. So that was kind of this idea of you can get a lot out of hydraulics, but they come with a cost in the form of weight. More recently, I said we kind of figured out probably how to do this, at least in some form that allows some level of scale, is this idea of direct drive actuators. What I mean by that is we want to keep the transmission low gear ratio, and that allows you to have this really low friction and low inertia in your system. So you get really fast, really powerful movements out of it. And this kind of really was first done convincingly on Mini Cheetah out of MIT. We have one at IHMC, which is a lot of fun to be able to play with, have it run around. But that kind of led to what we see now a lot of, and you'll see a lot of videos of this robot here on the right here in a little bit. This is a robot from Unitree called G1. And these are doing some incredible things at this point. And at its core, it's because of these direct drive actuators. But that's more of a recent thing that we figured out. We didn't use that in Nadia, so now I'm going to talk about what we actually did with some of our engineering. Nadia had pretty ambitious goals. You may be wondering where we got the name Nadia. We said we want to make this thing move like a human gymnast. We did not make it move like a human gymnast, just to break any kind of suspense on that. But our lead designer on the project was Romanian, and he said, oh, human gymnast, Nadia Comenici, I'll do it if you let me name it that. And so we said, okay, we want you here. And what that means is we wanted to be able to have human-like range of motion, speed, power, weight. We got there on some of these. We got there with human-like range of motion. We got there with human-like torque. Not quite on weight, though. Nadia is still a little bit big. It ended up weighing about 220 pounds. But we also said we're not going to try and do everything. We're not going to worry about hands. We're not going to worry about skin sensing. We want to do falls. We didn't quite get there. When we worked on this platform, we started really in 2019. You can see a lot of these 3D printed mock-ups here on the left-hand side, and we spent a lot of time working on it. And one of the things that was most interesting about the Nadia project is really around 2022, notice that's when we got our upper body, is when a lot of companies started saying, hey, I think that we can actually do humanoids, like at scale. And that's when you started seeing all these startups happen. But what went into Nadia? So the first thing was clever mechanisms. We wanted to get high range of motion. Well, that's really hard if you're going to use these hydraulic pistons. So we had to spend a lot of time on the mechanism design. You can see particularly is this hip joint, which is kind of what I'm focusing on this slide on the right-hand side. So we actually had two of these pistons going in to do both that hip pitch or flexion extension that you have, that picking the leg up like this. But then the same pistons went in to actually do the hip roll, this ab-add motion. And we had to do dual, what we call in the mechanism community, dual 4-bars, which, let me tell you, I don't want to work with those again. They introduced a lot of challenges. But they allowed for the robot to be able to pick its leg up really high and take crossover steps and do all kinds of things that we just hadn't seen robots do before, particularly not with linear pistons. Another big part of it was, okay, well, we want the robot to be able to survive falls. We want it to be able to get up off the ground again. We want it to be able to take all these impacts. And if you watch some of our YouTube videos, we showed that we could do this by putting it on a giant 2x4, lifting it up, and letting it slam into a piece of cinder block to make sure that if it accidentally kicked it, it wouldn't break. And that was a day, that's for sure. But we thought this was possible really because the feasibility proof is downhill mountain bikes. It used to be in the 90s, early 2000s, pretty much everybody used aluminum. It's kind of the prevailing wisdom on that. And previously it was steel. But then people started to shift towards carbon fiber. Carbon fiber is great. You can do all kinds of awesome things with carbon fiber. And if you don't know what carbon fiber really is made of, it's these carbon strands that are woven together. So you have some going this way and some going this way, depending on how you get your sheets made. You can also have all of them going one direction. And what you can do with that is you can say, okay, well, where's the stress going through this shell? So if I take this thing and I load it and I compute where all the forces are going through the shell, I can then take extra carbon and I can reinforce those lines. And so that's what we did here. And by doing that, you can see we actually reduced the mass of this thing by a lot. So that kind of showed you can do really lightweight shells that can protect things and maintain that strength, which was really neat, but they're kind of hard to manufacture. So we actually ended up having to do a lot of it in-house by hand. I don't really want to repeat that if I can avoid it. And but last, we did a lot with Nadia, but one of the things that we didn't do was untethered. And this is really because these hydraulic robots that you see, and IHMC is not the only one that's done hydraulics. A lot of those robots that I showed you earlier, those quadrupeds, like Big Dog and LS3 that we had pictures of earlier, they use hydraulics. What they did, though, for hydraulics is they took their pump, that moves all the hydraulic fluid through it, and they hooked it up to a gas engine, and they put that on the robot. That wasn't really an option for us, so we had to do an electric one, and we didn't have 10 years to develop one like they did, so we tried. And we were able to get a lot. We got 3.8 kilowatts. That's nothing to laugh at, but it was relatively big. And one of the things that we kind of said after this was, well, one of our main challenges was we want to be able to take this thing out of our lab into the real world. How do we do that? It's probably going to take us 2 to 3 more years to figure this out and a bunch more iterations. Let's pivot. Let's go to electric. So we said we're going to do electric just like everybody else. We're going to make Alex. So Alex is actually pretty cool. We've been working on it for a while. We wanted similar goals to Nadia, but we really wanted to emphasize this kind of outdoor urban operation. And one of the things that we really wanted to focus on for that was having this motion-informed design, so how do humans move as part of it, as well as let's leverage some of the best of these electric motors. So for that, the thing that we found that's really critical is this idea of rolling contact. So if you think about a direct drive motor, a lot of people use them. There's a lot of different gearboxes you can use in there. A lot of folks do traditional gears, so planetary gears is how we would call that. We didn't do that. What we did was this idea called a cycloid drive. So that's what I think this GIF shows really well. And the way that this kind of works is you basically have, this disc that's rotating. It's being driven by some input shaft. And then you have a different number of lobes on that disc than you do these pins here. And that difference causes an interaction force as these things spin, which then gets your gear reduction on the output. And the great thing about this is, whereas a gear, you can think of all those little gear teeth, they slide together. There's friction on all those interactions. It means you have these losses. They're inefficient, and then you feel it on the output. What I can do is I can basically buy the world's supply of bearings, it feels like when you assemble this, and I can put those in there, and I can get rid of all of that sliding contact, and now it's rolling. I have no friction on there. And you can get really, really high torques with really, really resistance in there. So you can get a platform that not only is really efficient, you have low losses across it, but also can feel all those interactions with the environment. You can actually see that here. We've taken a motor and we've attached it, and you can see my colleague Jared is just able to move this thing back and forth. And that motor does about 250 newton meters of torque, which is roughly what your leg can put out. So if you think about that, he's able to take a motor like that and move it as freely as you can move your leg. And then we can actually have it, if we turn on some compensation things in there, you can see that just gravity can move it with hardly any output forces, which is great. That means we're actually approaching human-like performance in our actuators there. And we're not the only people that do this. I just think that we do it better than everybody else, but that's an aside. We're also not having to make thousands of them, so we're able to kind of do each one by hand. You can call us like Ferrari, that's okay, I'll take that comparison. But our robots are more than just our actuators. So one of the things you want to think about, okay, let's say I want to take a robot, have it be able to interact in the world, move things around, manipulate the environment. That's one of the reasons that these robots are useful. You should probably think about how you design the arms, right? So what we do, and what a lot of people do, is you look at, well, hey, I can create this visualization of where the robot can reach. So this is actually what we call a heat map of this left arm here. And you can see that you can look at this color is based on the number of configurations I can put my hand at the end. And you know that if I really want to manipulate an object, if I have my water bottle here in front of me, I don't just want to grab it like this. I probably want to be able to grab it from the side, from the other side. That's what you want. You want to have a lot of those different poses. And you can see this kind of makes sense when you start getting near the edge of where I can reach. You can only get there from one configuration. So this shows that there's a lot of different ways you can manipulate the world. And this was a really useful tool to develop, because when we ran this and some of the other robots that we worked with in the past, like Valkyrie, which that had been made by NASA Johnson Space Center, we worked with them for a long time, we found that its best workspace was something over here. It didn't really have a whole lot of area in front of the robot that it could work with. Most of it was to the side, which meant that if you really wanted Valkyrie to be able to manipulate an object, it should stand to the side and turn its head. Probably not the best, particularly if you want to grab with two hands. But beyond just the arms, you also want to look at the legs. I think this is an area that often gets ignored in these robots, which is kind of surprising. I think the thing that's most unique about a humanoid is it has legs. You think people pay a lot of attention to this, but I don't think that that's always the case. And particularly, your leg is a pendulum. It swings from every step that you make. You want it to have as little torque necessary. I mean, if you think about it, if you've ever worn ankle weights, you know it takes a lot more force to swing your leg when you have all the mass at the ankle. So you'll see a lot of robots that are built where they'll have their hip pitch motor right here, their knee directly at the knee, and then both their ankle motors down here at the feet. We did not do that because we did the math and said that that takes about 3 times as much torque at your hip to be able to swing your leg then. If you want this thing to run, that's really going to add up. If you want it to operate for very long, that's going to add up. You need to make these efficient. You need to think about the dynamics of the system when you're actually designing it. And so we spent a lot of time on that. And that's kind of how we led to this design that you see here on the right. And beyond that, you want to eventually be able to put a battery. So I wanted to give a little bit of a sneak preview of the next version of the robot. The only real view of this you're going to get. So we're actually adding a battery on board so that hopefully in the spring we'll be able to take it outside. Maybe one day we'll bring it here. I don't know. Hopefully. We are going to leave the exoskeleton you see here in Ocala. Fortunately, we'll finally be able to start showing, hey, IHMC does do robots, not just pictures of robots. So this actually, we're able to just leverage drone batteries. So this uses a drone battery from an agricultural drone. Those things are huge. They're used to spray things like pesticides on crop fields, so they need to be big, so they need to have these giant batteries. We're able to put that on the robot and get 1 to 2 hours of runtime out of it. And when you put all this together, you can get a robot that can walk. This is the first time we've shown this video to the public. We filmed this 3 weeks ago. So this is our robot, Alex. We went over to the tech park, which is right near IHMC. We wanted to make sure to take it outside. Right now we have all the computers on board. We're talking to it over Wi-Fi. The only thing that keeps us from saying that it's completely untethered is we have this nice power tether right here because that battery's not on board yet. So we wanted to test the ability to go from concrete to grass and then operate outside and do all those things. So you can kind of see that here. And this is using the kind of control scheme that we've been really pushing at IHMC for the last decade or so. We developed it for the DARPA Robotics Challenge. We've been refining it ever since then. And what I can talk about with that is it's using this idea of simple models. And I like simple models a lot. And what I mean by simple models is I can model walking using what we call an inverted pendulum, which is like a broomstick that you're balancing upside down. And the reason you can do this is it captures a lot of the dynamics of walking. I can say it has a center of mass. The tip up here, people have a center of mass. It's going to be somewhere around your stomach. And then it has a center of pressure at the base. So that's right here. For a pendulum like this, it's really easy because it's just the point of contact with the hand. And you can think about this. If I'm standing and balancing, I move my center of pressure around as I shift my weight. I lean forward, it shifts to my toes. I lean backward, it shifts to my heels. Same thing with a broomstick. If you've ever tried to balance a stick like that, if it starts falling forward, you move your hand forward and you catch it. Well, walking is the same thing. You're just moving it from one foot or one hand to the next. And it's just this idea of doing that over and over again. And the great thing about simple models is that they're really easy for humans to interact with and humans to understand. So I can design it to work in all kinds of different terrains without a whole lot of changes to it. But if I tell it to do something, I know what it's going to do. I can understand and predict what it's going to do. And that's really important, that ability to predict and have that trusted interaction. What we do in our robot is we'll take my little stick figure here, which is a slightly less detailed view than the person on the previous slide. I can say, yeah, I have a pendulum. And I'm going to capture that. And I can actually take the position of my center of mass here. So where am I? As well as the velocity. How am I moving right now? And I can use that to predict future state. And so I can capture that in this nice little graphic, and that can tell me where I need to step based on that. And you can see that I was really excited when I got to do this on Nadia. It's using the same simple model here. The reason I was excited is not, I get to poke a robot. That's kind of fun, but also kind of terrifying. It was that I've been wanting to be able to have a robot that could actually do this for like 8 years at this point. Every robot I'd worked with was too slow before that. We had Atlas that was slow, weighed like 400 pounds. We had Valkyrie that was a little bit lighter at 350. They were just not quick or dynamic enough to do this. But Nadia enabled us to. And you can just see, I can take the simple model and I poke the robot and it's able to figure out where it needs to step in order to not fall. It is doing that with pretty bent legs. So this isn't exactly human-like. That's one of the things that a lot of people say as a comment is, well, it doesn't really walk like a person. You're right, it doesn't. It's not a person, it's a robot, but that's besides the point. I can make it walk more like a person, I think, and we'll talk about how people do that in a minute. But you can also go pretty quick. If I don't care about exactly knowing, moving my feet, the weight of my feet around, I can run these simple models through and I can do all kinds of dynamic stepping and more push recovery and things like that, just by picking where I want to step. But simple models aren't just useful for walking, which is great. I mean, I think that's a pretty useful enough thing as it is to justify using them. They're also useful for a lot of other tasks. So, for example, if I want to apply external forces on the world, so in this case, if I want to kick a door in, let's say I'm a firefighter, need to get into a building, I'm a soldier, also need to get into a building. It'd be really nice if I didn't have to rely on myself to do this. I don't know what's behind that door. I could be putting myself at a lot of risk in order to do that. It'd be really nice if I could have a robot do this. Fortunately, we can with simple models. So in this case, I can say, hey, I think I want to put a force like this on a door. Well, if I know that force, I know how much momentum I need to have at the time that I impact the door. And I can just plan backwards from there. I can figure out, well, where do I need to stand in order to be able to kick the door like that, in order to generate enough force there to have the momentum to not fall over. And then you can say, well, if I know where I need to stand, I just have to know where the door is to figure that out. And we can do this on the robot, actually. So one of the things that I learned, so I guess let me say first, in this, the robot saw the door. It actually used its sensors to figure out where the door was. And then we said, kick the door. And it determined where it needed to stand to do that, and then was able to kick the door in. And this was particularly fun because we had to custom build this door to be able to not fall over and then pile these cinder blocks up and everything. And it's actually kicking a door in. You can see the wooden hasp go flying as we kick it there. And one of the fun things that I learned after the first day of doing this is if you're going to be repeatedly kicking a door in, you should buy a solid core door because it was in two pieces. We actually have a slow-mo video, maybe it's this one, where the door didn't open, but it bowed at the top and bottom almost a foot before it opened. And then, we're able to tie this into the behavior architecture to make it do this autonomously. But beyond simple models, though, there's been a lot of advances in the last handful of years using optimization. So this can be machine learning, it can be trajectory optimization. We've really been able to do a lot of new things with this. And it's been really powerful. So I think that often these are thought of as two different problems. So when I talk about machine learning or reinforcement learning, what I'm looking for is a policy, so something that picks actions for the controller, for the robot to do, based on some state. And I'm trying to find some policy that gives me the best reward. So if somebody says, if you do this thing, you're going to get $5, and if you do this thing over here, you're going to get 10. I want to find a policy that navigates me towards that 10. And, we specify that reward. Well, optimal control is finding a control action, which is an action that seeks to minimize a cost. So instead of saying you get this reward, is if you do this thing, you pay me $5, and with that thing, you pay me $10. So it's the same problem in reality. You just add a negative sign. And so often these are thought of as two very different things, but you're actually solving the same underlying math. But the big difference is in reinforcement learning, you're usually computing this policy offline based on experiences that you're getting from a physics engine. So I simulate, you can see here, hundreds of robots, sometimes thousands of robots, being simulated doing different things. And based on those experiences, I'm figuring out what the best policy is. Whereas in trajectory optimization, I'm computing this online. I give it a physics model, and the robot's using that physics model to figure out what it should do as that would evolve in the future to give it that best reward. So this is looking at the past and saying, what have I done in the past that leads to the best reward? And this is looking into the future and saying, what should I do in the future to lead to the lowest cost? And I think that optimization, this idea of model predictive control, is a really powerful thing because it helps solve what we call this grounding problem, which is this thing that's a big problem in learning of, if I do something, how do I know that this is grounded in reality? How do I know that it's grounded in doing the right task? So here I have a great demonstration of people using MPC. This is the Atlas robot that you maybe saw doing backflips earlier. It's solving these problems, and then we've actually been looking at this on our robots, so standing here and then naturally balancing as well. And the great thing about this framework is that it can take all these different inputs and it can give you a physically real output based on that. And you're going to get to see it do a flip here in a second. And this is different because I have all these different inputs that can go into it. And that's great because that means I can be guaranteed on the output. I can add constraints and make it do whatever I want. Reinforcement learning is a little different. So here's a sped up video of us testing a reinforcement learning policy that we trained on a different robot. Reinforcement learning is different in that, in a way, a lot of the modern advances make it a lot easier. Instead of hundreds of thousands of lines of code, I have to write hundreds of lines of code. And I can just download this off the internet and train it. This was an intern that worked with us for a summer, and he trained that, as opposed to taking 5 engineers and having them work for a year and a half on the MPC stack. So it's really enabling. But one of the disadvantages is that your results are only as good as your experiences. I said that it's learning from experience. Well, here's a video of us having Alex walk on the right, and when we were training this policy, we didn't give it a whole lot of experiences of it walking slowly. So you can see when it starts walking slowly, it looks pretty bad. I'm willing to admit that. And then actually when it starts going faster, when we start giving it faster inputs, well, that's more what it learned over. So it's able to walk a lot better there at the end of the video. So I think that's really important, because that means that if you want to use reinforcement learning, you really need to capture what you want it to do and in the environments that you want it to do, whereas model predictive control, this optimal control, it's less like that because it's what they call generative. But it's also incredibly powerful. So I don't necessarily advocate for treating your robots this way, but you can see that using reinforcement learning, this robot is able to learn how to stand back up from the ground significantly faster than I'm willing to bet anyone in this room can do, including myself. And so you can get this incredibly robust behavior out of it. And you can also get really dynamic motion. So this is us having trained a robot. So this is what that kind of simulation environment looks like. And here it's running at, I think it was 8.7 meters a second, which is something like 19 miles an hour. So it's not as fast as an Olympic sprinter, but I think it's probably faster than I can sprint at this point. And I'm very excited to put this on a robot. But so you can get some really impressive results from this idea of reinforcement learning. But making a robot actually do something, making a humanoid actually do something, is a lot more than just a control problem. We've shown all this really robust control. It's a lot more than that. I want to have a robot actually do a useful task. And one of the things that we've found is that virtual reality provides a really, really powerful mechanism for doing this. So here, we have our pilot, John, off screen. He has a VR headset where he can see what the robot sees and then can control what the robot's doing with the TANs, and as he moves his head around, it will look that way. And he hasn't seen this setup before. So where I said reinforcement learning requires experience, he doesn't have experience doing this. He just knows, oh, here's a pipe, here's a barrel, I need to open this up and get some suspicious object out of the barrel. And he's able to take the pipe, use it as a tool in a way that he's never done before, and then actually reach into this barrel to get something out. And this is something that before VR we were not able to do at all. I will say one of the things that we learned in this is that if you're going to be doing routines where you're going to have something that looks kind of a lot like a pipe bomb because it's a fake pipe bomb, you should tell your cleaning staff about that before they come in and they discover something that looks like that sitting in your lab, because that may result in them calling the police. But VR can do more than just this task. This is really impressive. I'm happy we could do this, but it's pretty slow. You can also do it for dynamic things. So here we actually have Nadia playing Luigi in ping pong, and you actually have Dex here in the background controlling Nadia. So you can see the kind of inputs that he's using. So he's seeing what the robot sees and is able to respond to these tasks quickly enough. Now in this case, it's not a completely fair comparison for fielding it, because he's directly wired in. We have a wired connection in, so he doesn't have to deal necessarily with the latency of going over Wi-Fi, but it's still very surprising to me that he's able, because he has to be able to figure out where this ball is coming from, be able to identify where it's moving to, figure out what he needs to do with his hand, and in the meantime, send that to the robot, and then the robot has to be able to do it fast enough for him to be able to play this game. But you can also actually do locomotion, which I didn't think we could do. And here the robot has a model of the environment. You see Luigi again, and this time we added feet trackers, so beyond just hand trackers, he's added them for his feet. And he's just walking forward, and he's able to see where that is in this environment, and he's able to say, that's a good step. So this actually allows you to do really tight control of what the robot's doing on the fly. Which is great, because when we start talking about complex terrain, whether that be things like balance beams, piles of cinder blocks, what have you. We talked earlier, we want these robots to be able to go into things like disaster zones. Well, for that, they need to be able to move through a disaster zone. It's not just a smooth factory floor, right? Otherwise, just put wheels on it. We don't need legs if it's smooth. To do this, we first had to come up with models of the environment. So, early on, some people had tried footstep planning, but it wasn't really able to do it in what you would call real time. You had to have a good model ahead of time. Here, the robot is actually modeling the world using its sensors that you can kind of see down here. And what we're saying is everything's a plane, everything's a flat space. And then you're able to say, I want you to go here. I place a little goal, and then it figures out the steps that it needs to take for it. And that works for balance beams. It works for complex cinder blocks. We had to do this during the open house. But what's really neat is you can actually then take modern compute and put it on the GPU. Some of you have probably heard of GPUs, which allow you to parallelize everything. And then you can compute these planar regions in real time. So you can see down here, this is what the robot sees now. Instead of taking 20 seconds for it to build up a model of the world, it's able to do it just on the fly, which is great because that means if I change the environment, it can react to it. And you can actually get even better. You stop making the assumption that everything's a plane. It's kind of a silly assumption. Let's now instead, localize all that in height map. And you can have robots plan up and down stairs in real time. And this is great. We showed this in the lab, and this is kind of an example of how, these robots can move through complex worlds. So here we're just telling the robot, walk forward. Walk forward when you get to the top of the platform, turn right. And it's able to go up these cinder blocks, and then it's able to go over the kind of stepping stone pillars that we have, and then down the stairs. And we actually did this in our open house this last April, so that's when this was. Since then, like I said, we've retired this robot. It's been a little sad to see it go, but that's okay. However, I talked earlier about how I think the DRC was one of the most impactful things when it comes to humanoid robots. But one of the things that we also learned is that robots were slow. So given that was in 2015, we've gotten a lot faster then. But one of the core observations of how we got faster was, well, what made us slow? Well, yeah, they move slow. Atlas is a slow robot. But also, if I look at this plot here, 65% of the time, the robot was doing nothing. It was just standing there, waiting on commands from an operator from somewhere to know what to do. So I can work on making the robot faster, sure. But the best if I can do is speed it up. Let's say I make it twice as fast. This still isn't that much faster. Only a third of my time was spent moving. Instead, I can actually make this 3 times as fast by just having it move constantly. So we wanted to start on building these routines using human knowledge. And this is something that I think we differ a lot at IHMC and in our approach to humanoids is we want the human to be part of the operation. And so we actually built this architecture around that to allow a human operator to control the robot to do things like building exploration. And so you can see this with Atlas here. We told the robot walk forward, and when you see a door, tell us, and we said, yes, that's a door, open it. So the robot was able to then use its autonomy to open the door, and go through the door, and then what you'll notice is it said, I don't know how to get past this. I can't keep planning forward. There's obstacles. So then John, our fearless operator, can jump into VR and clear the obstacles. This is a task that's being accomplished together. It's never seen obstacles like this before. It doesn't know what they're going to be like. Instead of saying, oh, we have to design the robot to be able to handle every possible contingency, no. Just allow a human operator to jump in and help it, which is great for disaster response. But beyond this, that's a pretty limited approach. So we wanted to look at, well, what's more scalable? There's this concept from the literature called behavior trees. And the idea of this is you can actually model the behavior of how robots, or people if you really want, do operation as a tree of decisions, where every individual action is a leaf of that tree. And so in this case, I have a door opening behavior tree. The first one, get to the door. That's what this guy is right here. So first walk to the door, then reach the handle. Once you do that, do the next thing. So actually open the door, so turn the handle. And the great thing about this is I can collapse those lower elements of the tree. If I have a behavior that says open the door, I can now compose that into this higher level routine. I can just nest trees together. But we don't, while this has traditionally been used to make something fully autonomous, we didn't want to sacrifice the ability for a human to jump in. So we wanted to design it to have a human in the loop. And so a lot of interface design went into that. So we have this, you have the video of the robot actually doing this task on the right, and then what the operator is seeing in a user interface on the left. So it sees this virtual door. They can see these actions being done by the robot. And importantly, you can actually go in and say, no, don't do that. Pause. And you can change it on the fly. We can also actually make new behaviors on the fly so that if the robot sees something that it's never done before, I can write a behavior right there from this user interface so that it can do it again next time. Then, one of the challenges with this, though, is we're using these Aruco markers or QR codes on the doors to do this. Fortunately, other people that aren't us have spent a lot of time on computer vision. So a lot of machine learning has really revolutionized computer vision. And this has actually been one of the biggest breakthroughs in making these robots actually start to resemble a form of intelligence is computer vision. So here we have this system that's released public open source by NVIDIA called Foundation Pose. And what we do is we customize it using some fine tuning. So we have this auto labeler. So it basically goes in, we say, I want to know what these objects are. And it's able to gain all these experiences for that from real data and from our data. And then we can change the model so that it can recognize, it knows what the door is and where the door is. It knows what the barricade is and where the barricade is, which is great because now I don't have to add all these things for the robot to be able to figure this out. And when I incorporate this into my behavior architecture, my behavior tree, I can get autonomous doors. So in this demo, we basically told the robot, hey, find the person in this environment. And when you do, salute them. The reason we chose salute them is because I actually took our Office of Naval Research Program Manager, I went on Amazon and I bought a cardboard cutout of a Marine and I superimposed his face on it because I thought that would be fun for this demo. And we did do some scripting in here where we said, always go from left to right. In this case, the robot saw that there was an obstacle in the way, so it moved the obstacle. It opened the door here in a second. The challenge with Nadia is it didn't have a head. So instead of being able to look up, it had to lean its whole chest back to look up. And so then it opens the door, it goes in, it sees the Marine, and salutes them. And in the full-length version of this video, we actually then take this cutout and we hide it in the different rooms, and the robot then continues its execution until it finds there, which is, I thought it was pretty impressive. What we didn't do, though, with this demo is, there were some limitations in the fact that our coordination logic, the thing that we were saying, things like go left to right on the door, that's hard-coded. That's not really scalable in it. It also didn't really allow for a whole lot of replanning. We kind of gave it the sequence of events that it had to do. It wasn't very reactive. And that kind of took us back to the drawing board of how do we want to define this logic here. And I think this is a figure I'm going to allude to here in a minute. So really what we'd done previously was we had this behaviors, so open door, but if I want to have a thing like a goal, whether that be gain entry to a building or clear a building, that's just a bunch of different behaviors composed. So we wanted to put that at a higher level and then be able to add some additional tools to think about it. And what we did for that was we plugged an LLM into it, so large language model, where we said, hey, I want to do some task. Here are the behaviors that you know how to do. Figure it out. Give me the sequence of behaviors that you need to execute. And this actually works pretty well. So in this case, we told the robot, the goal was to open a door, to place a charge on a door to be able to, blow the door open if you needed to. So we told the robot, hey, go behind the barricade, retrieve the charge from the person, then go to the door and place it on the door, then retreat back to behind the barricade. That's all we told it. We didn't tell it. We actually typed it in. We just need to add a microphone for that. And it's able to do that. It's able to take these individual actions and compose them into a sequence of things that the robot needs to do on the fly. So I think what we can talk about, though, is when we start thinking about demonstrations, because we've done a lot of teleoperation data where we're giving a lot of this information to the robot. If you give this as demonstrations to them, they can do some pretty incredible things when you combine this with learning. So here, they took motion capture human data, they mapped it to what the robot looks like so that they knew if I wanted the robot to do this, this is what it looks like, put it in simulation, learn it, and you can do all of these crazy things. The problem with this, again, if you deviate much from that demonstration, the robot has no idea what to do. It will just fail completely. Of course, no one shows you that in their videos. There are approaches that people are starting to use to figure this out. There's a lot of awesome feedback policies you can do online, but that's still a huge open challenge in these robotic systems. You can also say that, if I have enough simulations, I can start to do these mid-length tasks like opening a door. So here, they have an awesome simulation environment where they're able to train it in order to open a door in that environment, similar to what we did. But they basically handcraft all these rewards. They say, oh, we're learning all this, it's intelligent, but you still had a person saying, do this, then this, then this, then this, and then you feed all of that into the simulator, and it does it. And they're actually having to program what that looks like, which is basically what we're doing already with traditional autonomy. And then when it achieves this, its results are about that of a person having teleoperated the task. It's not significantly more reliable. I mean, this is 80%, which is great, but if I have it 80% reliable and then I need it to open 20 doors, you can do the math on that. It ends up being not very successful. But also, this isn't doing work. If I have this task, and I think about this back from our nice little tree here, this is really just tackling this behavior part. It's not a goal. This isn't doing a shift at a factory. So if I wanted to do that, I then still have to have a user come in and stitch all of these things together and describe that task for it. And even though you have this as a capability, it still struggles. So this is the robot that we saw earlier at the beginning where we talked about robots in the home. This is Neo loading a dishwasher. And it takes about 5 minutes for it to be able to shut the dishwasher. And they're selling this to people. You can buy one for $20,000, which, I can't fault them for trying. I mean, this is more than what I've done. I haven't started deploying robots to people. It's not there yet, but what they do offer is if it can't do a task that you want it to do, a person can teleoperate into your robot and go into your house and do those tasks like a maid, which is interesting. They're going to collect all this data from your house. I hope you're all okay with that. And then use that to make their robot better over time. So if we take all of this and we talk about what we've learned and where we think it might be going, I think it raises some interesting questions. So is artificial intelligence on robots actually intelligent? And is it really able to execute missions or shifts or work or things like that? So here we go back to Figure's impressive deployment at the BMW factory. It knows exactly what it needs to be doing. Someone's told it everything that it needs to do from the beginning to the end. They spend months programming this. It takes maybe an hour to train an employee to do this. I don't think that that's actually intelligent yet. It's not really making decisions. It's doing exactly what you told it to do. Now, maybe that's what you want out of your employees. I know sometimes we struggle with that too. But still, this isn't a thinking machine. And then if you think about, okay, well, let's say you put AI on your robot, which is what everybody tends to do now. They say, oh, this is AI powered. And their hope is that you say, oh, AI powered, awesome, it must work. If we put that on our humanoid, like what we just saw with Neo here, does that mean it's solved? I'd say no. And just because it's AI powered doesn't mean that it's there yet. There's a lot of potential. The future is bright for it. But if we start thinking about what it's good at, these tasks need to be really well defined. I also need to be able to get a lot of data on how to do it ahead of time. With the current approaches, I don't think that that's great for what we really need robots. So we don't really have our Rosie the robot from the Jetsons yet. You don't have this awesome home assistant that you tell it anything and it can do it. It can figure out exactly what needs to be done, whether or not it's seen it before. Really, this warehouse logistics stuff is what we're at with the capabilities. Now, maybe we're going to be able to get there. We'll see what's next on it. But what I struggle with on a lot of this is, again, I don't need legs for this. I can do this with a wheeled base. I can put a giant battery in it so it can last an entire shift. I can load that thing down. I don't have to worry about it falling at this point. A lot of these work you don't need these legs for. So what you're seeing these robots be sold for, raised for, is the promise of that potential of the future rather than what they can do today. And if I start thinking about what they're going to do in the future, a lot of people talk about is we want to solve the dull, dirty, and dangerous, the 3Ds. That's what we want robots to be able to do. I think that the area that we need to be focusing on is the dangerous ones. So if I think about bomb disposal or confined space entry, people are the only things that can do this currently. You're not going to be able to do this without legs. You're not going to be able to do this with most traditional robotic solutions. The only thing, and if we didn't have to have people do it, we wouldn't have people do it, because if I'm sending a person into a chemical tank to do inspection, there are 3 people standing outside to make sure that that stays safe, and they're all getting hazard pay. This is an extremely expensive task outside of just being really risky. So if I think about where we're likely to see these, it's these dangerous tasks that offer that really high reward, assuming we can get enough people to adopt it. Because at the end of the day, it's the economies of scale that drive these things. Because if I'm making you 10 robots, they're going to cost a lot of money. But if I'm making you 1,000,000, they get a lot cheaper. And that's what really people are promising on this. With that, I'd like to thank you all for listening. Open the floor up to some questions. Have my video play. Oh, they didn't know it was coming, so that's fine. Well, I look at this nice timer on my laptop here, and I see that it's 6:03, so I figured I should.
Notice. So do we have questions here? Any questions? You guys, okay. I see you. Hey, Tom.
Hi, Lori.
How are you?
Doctor, thank you very much. Lately, we've seen some serious hype about robots from Mr. Musk. My question is, are you investing in Tesla? Do you recommend I do? Or are we just seeing hype?
I don't think I'm qualified to give investment advice. I think what's an interesting thing is if you look at the value to earnings ratio of traditional car companies and compare that to Tesla, they're pretty different. And I think that's really because they're trying to make this big pivot into being a robotics company, and they're putting a lot of bets on that. So usually it's like a 6-to-1, they're a 360-to-1. So I think that's an interesting thing. So maybe if I'm talking about investments, maybe I wouldn't do it for that reason. But yeah, if it's possible, they're positioned pretty well. I mean, they're one of the most valuable companies in the world. They're able to get a lot of talent, and they're able to work that talent incredibly hard. I don't know if it's there yet. I also think that one of the challenges is going to be if you think that it's there based on the video that Tesla releases of the robot working on the factory floor, they're going to get a significantly high stock bump. So it's going to be hard to really tell from exclusively Tesla whether or not the technology is there. But, I think that if we're possible for manufacturing, there's a good chance that Tesla is going to be able to do it. I think that they have a lot of competitors, and that with the advent of a lot of this open source technology that's coming out, a lot of those competitors won't be very far behind either.
Hi, Robert.
Hi.
So you were advocating sort of for this humanoid robot, and then the first part of the talk, you talked about the mechanics of a humanoid, the bipedal parts and the direct drive motors. And towards the end, the other important part of the humanoid is the intellectual part. And you started briefly talking about that, and you got the agentic workflows. I'm curious about, if you're going into these dangerous settings, I'm curious what you think the future for causal reasoning, right? You send a robot into a fire, gets to a door, how's it going to have the reasoning to say, hey, if I open this door, it might interject oxygen, it might have blowback. I know the human in the loop helps that, but
Yeah.
Where do you see the vision for this causal reasoning on these?
So I think that's actually a great question that you're bringing up that's getting kind of ignored in a lot of the generative AI startup technology development world, because they're all invested in LLMs, which has no cognitive models, doesn't really understand cognitive reasoning on a lot of it. And I think that there's a lot of skepticism as to whether or not they ever will. That's not really my research area, so I could be wrong on this. But my understanding of it is that it's unlikely that the existing approaches will be able to do it. However, there has been a lot of traditional research on those kind of cognitive models and reasoning that I think is going to play a strong role. But for me, taking a step back, what we try and do is we have a human be part of the decision-making process. So as opposed to saying, I'm sending a robot into a mission-critical scenario, I don't want it to operate completely autonomously. I can actually, if it's like, I don't know what's going to happen if I open this door, get help. ask a person. You don't have to figure it all out on your own. That's how we typically engineer most of our actual human systems, is really strongly around choreographed teamwork where your different teammates are people doing these tasks. Why should we expect our robots to be functioning differently? If anything, they can share information faster and better than humans can, so why can't you have that kind of interplay with them in a human system? So that's really where I would hope to see these systems go, is instead of saying we have to rely on these robots to figure it out completely on their own, because we have no idea how to do that yet, I would say leave a human as part of it. Have a human operator be operating a fleet of these robots or something. As long as you can get that ratio for a lot of these things down from 10 operators for one robot to 1 operator for 10 robots, which would be great, but even in disaster response, I'm willing to have 1-to-1, I'm willing to have 10-to-1, as long as my 10 people aren't having to go into these dangerous environments. That's a win.
You have one here?
Yeah.
I was wondering if there was a, I guess, ideal power source for humanoid robotics at a scale such as the demonstrations, or at a larger scale.
So I'm assuming you mean like batteries? Is that kind of, when you're talking about power source, are you talking more the powertrain as it relates to actuation?
The power source.
Yeah, so I think that right now we're pretty limited to lithium ion or lithium polymer type batteries. That's what we see in a lot of autonomous vehicles. And we're able to piggyback off of the investments that are made for autonomous vehicles to do that relatively cheaply compared to what we were doing 10 years ago. But there's a lot of research in this idea of like breathable batteries. So one of the great things about internal combustion engines is they're not having to carry all of their energy-making matter with them. They pull a lot of that from oxygen in the environment and the air around them. So if you can actually have your battery system pulling from the environment around it, as opposed to LiPo, you're embedding all of that in the battery. It doesn't get anything from the world around it. That's really where we want to be moving to. I don't know how far off that is. I'm also not a battery scientist, so. I keep saying that a lot, like, oh, I know some about a lot of topics, which I feel like is pretty general in robotics, but I feel like I keep punting on some of the more specifics on some of these.
How do your humanoids do on bouncy castles or trampolines, balance-wise?
Very, very poorly. When you develop a lot of these controllers, what you're assuming is that if I exert a force on the environment, that's the force that gets exerted back on me, like stiffly, so like on a floor. And you're not modeling those interaction dynamics, which was actually, for this here, a huge challenge as we went on the grass, because that's way different than concrete. What I'm hoping is that that's an area where some of the stuff that we talked about with reinforcement learning, you can capture some of those dynamics in varying your environments. But really, I think a lot of the promises with that is less on capturing that via prior experiences and more learning how to adapt to it over time. So think about this from a classical perspective, there's two kind of dichotomies of robust control and adaptive control. One was be robust to anything that may possibly happen to you, and the other is adapt to all the things that do happen to you. And if you say I want to be robust to everything, you end up walking with your legs really wide because you think that you might constantly get pushed or something like that. That's not great. And you actually see that in your RL training. If you actually apply a lot of these disturbances, you get those gaits. And so if I were to model all those dynamics into it, it's going to walk funny. But if you can actually capture it and allow it to adapt online, instead of it being this fixed policy that it determined offline, you actually allow it to change through experience on the fly and adapt to the things in the world around it, you may start to be able to get some of that kind of capability. And that's where we're starting to move as a group and as a field as well. A topic I knew something about finally.
Okay, we have a couple more here. We're going to have time for maybe 2 more questions. So I think I have, okay.
So when you move into the teleoperative mode of that, what is the acceptable latency values that you're dealing with?
That's going to depend heavily on the task that you're trying to do.
Okay.
So if you think about a task where if you stop providing inputs, everything stays still and doesn't change, latency inputs can be whatever I want them to be. But as the task itself gets to be more and more dynamic, you have a lower time constant, as we would call it, that latency requirements get a lot smaller. And one of the ways around that has been a continuous challenge is how can you forward simulate locally what will happen based on your inputs, so that even though you have this latency, you can be approximating what the real world is going to do, and then just do this kind of synchronization. And that's actually a big challenge that NASA's been tackling, because as you know, if I want to operate something in space, in orbit, much less on Mars, I'm going to have huge latencies in my system. And so being able to adapt for that kind of changes is a real challenge that's being focused on.
So that's all through algorithms that you're anticipating what is the next move within the next sort of milliseconds, right?
Yeah, so that's what we do, because we're only dealing with tasks that have relatively low latencies. This doesn't translate to those kind of space domains the way we do it, but the way that they're trying to move towards is having those kind of simulations, or what they call digital twins, that can do that.
Thank you.
Oh, the same question. Okay, here you come. Okay.
I just had a question. I saw on social media a robot recently fall flat on its face. I guess it was the Russians. I was wondering what your opinion was on that. What caused that? Why would they display this, and why did it fall? Did they not do the testing like you've been doing?
Well, I mean, our robot, if I showed you the unedited version of this video, it fell quite a bit.
Okay.
We just didn't take it on stage and have it do that in that setting. I think this happens. A lot of the Boston Dynamics robots have fallen flat on their face. There's a great video of one head diving off of a stage by accident and completely caved in the front of it. It can happen. I think that's more of a management decision. Why did they choose to display the robot despite not having given their team enough time to more thoroughly test it?
Okay, I was just curious on that, what your opinion was on that.
I feel for them, because I've been there.
Okay, thank you.
Okay, we have, Brian. Here, all right, one last, I'm sorry, you guys, we're going to have to, one last.
Do you have an opinion how the technology in the U.S. compares to, say, the Asian countries or Europe?
That's an interesting question. Oh, there we go. I think I wouldn't necessarily compare the U.S. versus Europe, because we work together a lot on that. So a lot of the stuff that we've talked about with reinforcement learning was really made possible through some innovations from places like ETH Zurich. I think some of the differences, if you start talking about Asia, there's a couple of distinct different groups there. I would say there's China, Korea, and Japan are the three that I'd really point out. Japan has been one of the most major players in robotics in the last couple of decades. So it's been really interesting to watch them not necessarily keep up with a lot of the recent advances. You don't see a lot of technology coming out of there. Whereas Korea doesn't look at this as a competition between them and the US. They just buy American companies. So Boston Dynamics is owned by Hyundai. And they've done a lot of this. So they work with us as opposed to competing with us. And they also have a lot of excellent research there. I talk about the DARPA Robotics Challenge, and I said we came in second. KAIST, a Korean university, came in first. So it's a lot of excellent work coming out of there. Where I think the most interesting comparison part of it comes into play is that China won, because I think they're able to manufacture and produce this significantly faster than we are. So there are, I went to a conference in Atlanta in the fall, summertime, and there were dozens of humanoid companies there that I'd never heard of before. There are over 100 in China that I think most of us would never have heard of at all. Some of them have literally built thousands of humanoid robots. So that Agibot that I showed earlier that was working on the car, they just finished building 5,000 of those. And I think that really points to they have the supply chain component of it absolutely nailed. Most of our electronic components come from China. Most of the machine shops in the world moved to China. So from a supply chain aspect of it, they're able to iterate a lot faster than a lot of us, and have also figured out how to make these systems really reliable, which is what the researchers need. Now then there's the research side of it, and I think that to say that China hasn't made enormous strides in that domain in the last 2 decades, and they've been really focusing on a lot of their investment at a national level in developing their universities to be able to compete with Western ones. And they're able to do it now. I mean, some of the great papers that are coming out are from Chinese universities. It used to be 20 years ago, if a paper was written by a Chinese university, you could kind of dismiss it in a lot of ways. They weren't quite to that level. But lately, they've been just as top tier as any of the other ones in the West. Which does lead to this interesting aspect of, well, how does that compare from an economy perspective? Are they able to do national initiatives a little bit more effectively than the United States is because they have a different economic system where the government is able to dictate a lot of this, whereas in the United States you're able to have potentially faster innovation because it's a little more open. And I think time will tell on that as to which system kind of works a little bit better for some things like this. But it's also an interesting one because so much of what they do is leveraging what we do in the way that publications work and open source works. So it also doesn't exist in a vacuum. You know, as soon as they release a video, I can go online and I can see the robot and I kind of know how it works. So really a lot of this boils down to is that supply chain problem, which we've prioritized as a nation. You know, we're focusing on developing that supply chain, redomesticating that supply chain, as well as looking at other key geographical partners for manufacturing like Mexico, Central America, South America, in order to build that up to be able to not be so reliant on the Chinese supply chain. So that's a whole really long non-answer to your question, but I hope that it does maybe add a little bit more light to some of it.
All right, you guys, thank you so much for being here. We wish you all a wonderful holiday season. Please be safe.